Okay, if you're watching the last video, apologies about the stoppage. This will finish it out. We got to the moment of inertia, lambda L cubed over 3. We're almost done. Let's put in what lambda is, which is m over L. And I'm going to get the mass of the rod divided by its length. That's my linear mass density times L cubed over 3, which gets me mL squared over 3. Now, what we've done is we've calculated the moment of inertia of some rod of length L and mass m about its end, right? And it turns out that if you look up on the chart, which we do very frequently, what the moment of inertia of a thin rod about its end is, you get mL squared over 3. We very often look up simple objects on charts, but this is how you actually calculate it. As a way of just kind of convincing yourselves that this actually works, let's do this same problem again, but about a different point. So I'm going to start here again. But I'm going to pick out the point in the middle now. Right? Now, if that's the case, then I'm going. This invites me to set up a different coordinate system than I did previously. So let me cover up that work. All of this is still the same. My linear mass density is still the same. But now my origin is here. And so that invites an integral that runs from minus L over 2 to L over 2, right? If my origin is here, I'm going to have to integrate the whole bar, but this is minus L over 2, and this is L over 2 of r squared dm. We've already taken care of that, so I think we can skip to x squared lambda dx, where x, or my role of r is being played by x because I want to go along the x direction because this is horizontal and that makes sense to me. I know what my lambda is, and then my integration variable again, because I'm going in the x direction, is dx. All right, so now I'm going to integrate this. Lambda gets pulled out, lambda, which means I still have the integral of x squared dx, which is just x cubed over 3. This time I'm going to evaluate it from minus L over 2 to L over 2. So it looks like I'm going to pull this out, lambda over 3, and that's going to be L cubed, over 8. Not sure why I wrote that up there. Let me do that a little bit cleaner. I'm going to get lambda over 3 times L cubed over 8, and then minus L over 2 cubed gets me minus L cubed over 8. So that's a minus, and then minus, because when I cube this, I still get a negative. So this minus comes from the fact that I'm subtracting the lower limit from the upper limit. This minus comes in because I'm cubing a negative number, and I get minus L cubed over 8, which is lambda over 3 times 2L cubed over 8, which is L cubed over 4. So it looks like I'm going to get, when I multiply the 4, I'm going to get here times 3. I'm going to get lambda times L cubed over 12. And then recognizing that lambda is m over L times L cubed over 12. I get mL squared over 12. Now, if I look this up on a chart, what is the moment of inertia of a thin rod about its center? I'm going to get 1/12 mL squared. Let's compare the results we got, shall we? For the bar, let me do this like this. For the bar about its end, I got mL squared over 3. For the bar about its center, I got mL squared over 12. Both of those match up with what I can look up on a chart. I got both of them by doing the same calculus procedure. In general, you need to understand what we did in the calculus. And I found that usually the misunderstanding comes in here, expressing the mass in terms of spatial variables. It's just something you learn how to do. What this actually looks like turns out to depend on your coordinate system. If you're doing a differential volume element, in Cartesian, that's just dx, dy, dz, right? Length times width times height. But in cylindrical and spherical coordinate systems, it's a bit more complicated. But the upshot is, if you can do this, if you can understand what this dm means when I express it in terms of its density in some spatial variable, you are well on your way, both not only in this class, but in physics 2, where you will be doing that a lot when you're calculating effects of charge density.